Hello Internet, welcome to Fun Project Monday on Tuesday. Yes, it's the live stream where we design something electronic, currently an LED controller, without, let's say, the unpleasantness of a work environment. No project managers, no deadlines, no stress, we only have fun. And I like doing my electronics early in the morning. It's 5:30 at my place. Prime time everywhere where it matters. Everywhere where you're watching. I got some beverage, some coffee. I like coffee. And yes, we're going to dive in right after I've taken something. Okay. Let's take a look on what we were doing last time. Last time we were working on this portion of the controller. So on our power stage, we calculated some resistor values, put some ballpark values in, did the work of putting in all the part numbers for having the option of automatic assembly at JLC, so having all the SC part numbers inside, that's important. And that should be good to go. But today we won't work on this. Today we will work a little bit on the control circuit, which still needs to be populated. We're going to use Raspberry Pi Pico. In the first revision, certainly a Pico W prototype, Pico W module. And yes, I will dial that down, that looks too loud. That's better. Almost. Let's keep it like this. Yeah, that looks good. We're going to certainly use a Pico W module. And the problem is, yeah, we certainly need to populate another buck converter. It is it is an option to use the same one we will use for the power stage, because if you get a few more, it gets only less expensive. Oh, we should take a look if it's really that good of an idea. Let's check something down here. Okay, OBS is broken, but I certainly don't care that much about it. Let's take a look. Where were we? We wanted to check if it's viable to use the same power controller or use a different one. Nope, I want to have this one, yes. So in the design we are currently using an TPS, do I have it here? TPS 54302. And it costs 55 cents, 33 cents in quantity. I don't know about this. Are they the same? Yeah, there certainly have different part numbers, but they could be the same, and we pay 22 years. Yeah, let's say, so we certainly have to think about 30 to 40 cents. That's a lot. That's a lot. We want to minimize that. So let's look for some kind of linear regulator as an option. So I have no. Let's take a look. Connectors. Nope. 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 Power supply chip. Some linear voltage regulator. We want to have 5 volts out. And let's see, and we see that we are at a very yeah, I have to be careful. That's one. It's not 5 volts out. Oh no, that's the minimum input voltage. I want to have the output voltage set to the right amount. So output voltage. Five volts. Let's see if we can use a fixed one. That's okay, that's okay. Everything to 5.5 is acceptable. And we won't have the cheapest. Yeah, that's certainly the cheapest. And we have some LRH341A. No idea. Never heard of it. Let's take a look on what kind of part that is. Never seen this package. What interesting package, yes. Yeah, looks pretty standard, nothing. How much current does it provide? Of course, we would need a certain amount of current for 100. That's not enough. That's not enough because we need to power some LEDs from it. We'll need to power some the Pi itself from it. Let's say half an amp. Certainly, or most. Yeah, I think most would have half an amp. So let's take some of this range, because the Pico itself has an regulator itself. Well, let's take a look how much does the Pico draw. Power consumption. Let's take a look. Okay, popcorn. I have no idea what a popcorn test is. Okay. Okay, that's so we have to think about having to provide 100 milliamps with a few LEDs that say 300, 400 milliamps. That would be the top. Yeah, so that's the range of power supplies we should be looking at. And let's take a look. Apply pricing. And the cheapest part is an semi device. No, of course not. That's not SMD. It's not SMD. And okay, Wuxi iCore. That's correct. So the cheapest part in stock is a power silicon device. Never heard of them. And here we have a non-SMD part. Okay, let's take a look at this one. We haven't got an English data sheet. Okay. Okay. Yeah, that looks good. How much input voltage is allowed? Let's take a look. Okay, certainly a lot of overhead for the input voltage. Yeah, we could use that, no problem. Oh, wait a minute. It has 6 volt. Okay, that are the certain types. Okay, now I understand. So we could certainly use that one. That's also a standard case, so we can build it fast into our IDE, EDA. We should use that. Yeah, certainly. And it's cheap and plenty in stock. Yeah. Sounds like a deal. So let's head back and put this part inside the IDE. Because I'm pretty sure that this part will not be... Maybe it is. Let's take a look. Components. Oh yes, that doesn't work. PS78 M05. Let's take a look. If it's available. Maybe we are lucky. Certainly, I don't know. Okay. I don't know, is that okay, it sounds like a Chinese company. It's a Czech company. Is that the same power silicon? That's in use. Okay, I think the name power silicon is used multiple times. Do I have products? No, we have no products. And we have no part in the trace. While that's a pretty standard part, we should put it in very quickly. Oh no, we don't want a pattern. Pattern is an SOT23, so nothing special. That's certainly very fast. We will add it into our JLC library. It will be, or the my JLC library. It would be the easiest option. Alright, new components. And that would be an PS7 8M5. Ref design is U, value, power silicon, and the data sheet. Not of importance. That. Let's take a look on the data sheet again. And let's see the pin configuration. It's important because I want to know if the tab is connected to ground or should be connected to ground, or what the requirement is. Okay. Okay, no information if you should connect the tab to ground. Was probably that should be the case. I would assume that right now. So we go back. And add a few pins. 1, 2, 3. A little bit smaller, doesn't have to be that big. Then this will be pin 1. Name is input B plus. Yep. And show name, please. Oh, let's call it input. That will be the output. That's defined as pin 3, that's correct. And also please show name. And we'll have our common grounds. Okay. Let's together a little bit nicer. And this one should please be. Can we change that? Yeah. I want to rotate this one. Okay. Make it a bit smaller. Because there's no need that it's so big. That's okay. And we will add the JLC part number. Save that. Want to have the part number LCSC. Yeah. Add. LCSC, and part number is, let me take a look on the sheet, is C 300 8 to 12. 8 to 12, okay. So that will be certainly okay. We will add the pattern. nothing special, so everything is good. What kind of pitch does this package has? What kind of pitch has the package? Is that specified in some way? And if you take a look, that will be an nope. Is that specified? No, it's an SOT89. So now, question is what kind of pitch does it have? What's the standard pitch for an SO809? Ah, not that one. 89 was it? Was it? No. Yeah, SOT89. As a Wikipedia? Yes, that's a Wikipedia. SOT893. So after Wikipedia, that should be a standard pitch of G and 1.5. So then we'll simply choose that one, SOT89. And after that, oh, it's certainly a very common package. Let's choose one with a lot of clearance and white pads. Of course. Yeah, that looks good. We will choose this one. Okay. SOT inputs number 2 and 3. That's correct, I suppose. 1, 2, 3. Yeah, that's correct. Okay. Okay, now we can use it directly here. And say 30 cents. Actually a lot more, because we don't need to add the outside components. Good. Now we can add all vignettes and some capacitors. We already have used these 22 microfarad capacitors, so we certainly continue using them. Because, yeah, bomb consolidating. Okay, didn't copy it them. Oh, here we are. And here was the other one. Oh no. So these will be called C47. Or, man, who cares? Who cares? So simply add those. Here we will have not that big of a hassle with taking the correct capacitor values. There is a formula to calculate the right amount for capacitors, especially if you're considering excess voltage ripple. But in this application it will be more or less trivial. So we don't have to think as much about it. I'll simply take the capacitors that I have. And of course, you can choose the right values way more sophisticated. But most of the time you won't get that much. In this application, doesn't matter. It really doesn't matter. So we'll take a ground. Take a ground, and we have a V plus. 5 volts. What did we use for the input voltage here? Plus 24 volts, okay. So we'll certainly have a lot of capacitance in hand to correct all the voltage ripple from the power supply, especially in the near the power regulators. So I have no worries whatsoever in that case. Then we will add some smaller capacitance that we already used. That's too big. Yeah, the 100 picofarad. We'll use those at the front panel to reduce the amount of... Oh, come on. To decouple the shift registers a little bit. They should have some sort of capacitance near them. Okay. I will put them we will add them in series. It doesn't matter how we will put them on the schematic, and from the look of the schematic, it's obvious that we want to add those capacitors to both of these parts. We put that down. That looks a bit nicer now. Okay. Then there's nothing else on this PCB that we should decouple. We can add some capacitance to the plus 5 volts here, to have at least we will add some capacitance to the plus 5 volts to some higher capacitance. To decouple all the, let's say, all the switches at once, or all the LEDs. It's not really important, but we'll do this so we at least have a footprint to add some capacitance, and that it will be a bit easier. Okay. Good. And that's done too. And then we can add the plus 5 volts here too. I think that should be V-bus. Yeah, that is V-bus. I'm not quite sure. Let's check that again. For that we want to go into a browser. And let's take a look at the Pico datasheet. To make sure which because I'm not sure what the difference between vsys and vbus is. You certainly have, my god. So let's take a look here. My first guess would be we should use vsys, but yes, let's check that. vsys maximum is 5.5 volts, so we should use vsys. What's vbus? Can we have 5 volt IOs? Let's take a look. Vbus, oh, okay, so we have here some kind of voltage drop. So the bus is okay. So we should connect to the bus. Yeah, vbus, yes. Or, okay, let's take a look on that. Mm-hmm. Okay, there's certainly no reason to don't use vsys. We use vbus. Yeah. So from what I understand is that a vbus is protected better with a Schottky diode, and from where there is a voltage divider which helps monitoring the voltage, and it doesn't matter if you feed it like that or like that, really. Yeah. Oh, is that no, it's not. Okay. But yeah, that information is not really important to us. So, okay. And we will give the Pico, of course, 100 path of decoupling. That should be certainly done. Although the module itself has some decoupling, it should be good practice, or it is good practice to have at least some capacitance, at least the option to add some capacitance. And put this down here. And we'll add a ground. Then the 3.3 volts will be, of course, be added to the 3.3 rail. because we'll use it for all the shift registers and the buttons. That should bring enough power. Okay. So that and that. So these two pins are not important. That's the debugging. We'll put that to some header later. And now we can add all the I/O pins. So now it's pretty easy. The good thing about changing the screen, the good thing about is these I/O pins are extremely flexible. All the I/O pins have a PMW interface. It's great. I need to show it to you. I really do. All the pins have is it here? No, not in this data sheet. Let's change to the RB 2040 datasheet. So, BMW. Oh no. PWM, of course. Simply shift through. I think it's shown here. So every pin has a PMW interface, and two pins share one comparator, or two pins share one counter. So of course there are, I don't know how many 16-bit counters in this, 8 counters and 16 comparators. So the only problem would be if you're trying to use 16, and the only problem you would encounter would be if you are using multiple, if you have an application where you need multiple PWM signals which are completely latched together. But that's something you could solve with the PIO interfaces. So it's not that important, and we'll pull up one pin out again to see if there's something we don't. That's good. To see if there is something we. I'm not going to use that side. Thank you. We'll use W. We want to check if there are some pins with functionality we want to preserve, but that's not really the case. Maybe you want to preserve the 28, 27, 26 pins to add monitoring of the input voltage, or to monitor the voltage of the output. So we could do that as a failsafe and to detect overvoltage, or to detect if our device has too much load and we need to shut down, or reduce the we need to reduce the output brightness to save our device from shutting down. We could certainly do that. Yes. And then we can, so we want to preserve that, and then we can add all the nets from the first power stage and get that down. Start with channel 1 change voltage. And that's the reason I like to use these nets, because it makes things so much easier. So to have channel 1 blue. Let's do that systematically. The first one would be, we want to change the voltage. Now the first one would be enable. Because we don't have the problem of because we don't have a problem of having that kind of special input. We can go very systematically. Oh wait, do you really want to go systematically? We should do it the following. We should do the following. We will first of all check, do we have enough I/O pins? That would be certainly the first thing that we should check. So I have 1, 2, 3, 4, 5, 6, 7 control pins per channel. So we would have 21 in total for the pins themselves. Then would need to, okay, we would need to use one shift register for the time uncritical applications, because otherwise we wouldn't have enough, we wouldn't get enough pins. So we'll take one of them. Now we do it. No, that's a part I added myself, yes. So just go back to my library and add one shift register. Or we can try to do some dual inputs. We could try to add dual functionality to some inputs, but I don't think that's possible as far as I'm concerned. Simply an enable, one change voltage. Can we do that? No, I will simply add them. So we'll add for first and firstly add a shift register. Because that won't add any more pins, because we'll certainly use. So we will certainly connect, daisy chain that shift register with the other ones, so we have no problems whatsoever. And we said we wanted to, of course, change the screen. Always change the screen. So we certainly want to preserve pin 28, 27 and 26. 27, 26. We will use 21, 22, 21 and 20 for the shift register. What? Okay. The OE and MR, because we don't want to have an OE is put low and MR is put high. So we'll put that a little bit further here. So again, OE is low and MR is high. Certainly use a lot of these symbols, because it's very because it makes schematic clean to not to not have the requirement to always connect everything with a wire, because it certainly doesn't win that much. So that's so like this. Come on. Come on. I got so, and that will be shift out. Connect to net, shift out. Shift out one. And that one will be connected to one of the connectors here in the aftermath, in the next stream, I think. We can connect those now. So we will add to net. We'll certainly change the enableds here. Channel 1 enable voltage. Then we'll have channel. We can put all the enable voltages here. Add channel 2 enable voltage, connect without wire. And add channel 3 connect voltage. Plus. Enable voltage. Okay. Then we can have a change voltage pin here too. So add to net. Change voltage, because that's also an operation which is certainly not done in high speed. Channel 2. Change V. And channel 3. Change V. Okay. And that's all the slow speed stuff. And up here we can add all the PMW signals. It would be the easier, actually it doesn't matter. In the end it only would be a naming convention thing. And thinking about what kind of offset to use in the program itself. GB, add green, add to net, connect without, yeah. And we have channel 1, blue, blue, okay. And then do we okay, and then we can add all the other channels too. Another one, channel 2, red, V plus, channel 3, red, okay. Channel 2, green, yes. Channel 2, green, yeah. Oh, then we need to channel 3 green, of course. Okay, and blue. Okay, I messed this up, so let's make this channel 2 and channel 3. So, when we need to think about the front panel and what goes to the front panel. So, on J22, we have the 2 quadrature outputs. We will add those 4 and 3. 1, 2, 3, 4. Yeah. J22. 3 and 4 are the quadrature outputs. And here. I want to delete the So yeah, that's better. Then we'll rename those 2 nets to the name of the input of the display name. And so to do that, we will display the name here at the pins. Display name and display name, and rename the net to match the output or the input on the shift register. So that will be SHCP, shift SHCP, and that will be shift STCP. STCP, great. That we will add to the connector J2, so J22 pin 5 and 6. 5 is STCP. So shift STCP, okay, and shift SHCP. Really? Name's so similar. SHCP and STCP. Okay. So store and latch are added now too. I can add the voltage here too. So we have 5 volts on 8, 3.3 on 7. So we'll add those two. And 3.3. That was 5 on 8, right? Yes, and 3.3 on 7. So, like this, please. Thank you. And I don't like those. I certainly don't like those. Delete wire. Oh no, we will keep those and display name. Now we'll add them to the net, to the correct net. No, we are not allowed to add them to the net, otherwise would be quad out 1-1. Can we add those to the same net is the question. If we add those to the net, yeah, we can add them to the same net because we are on different PCBs. Effectively. So we can do this. And otherwise we'll change it later, that's not the problem. So we'll add this to the net quad out 1. Why can't I choose the right? Yeah. And quad out 2. And we'll certainly display the names. And one is simply ground. We'll copy that 1, 2. On that height, that's good. Go on, so that connector is completely populated, and now the second one. So the second one, I found an error why I couldn't use simply 6. Why I couldn't use simply 6-pin connectors, because I didn't thought about putting the switch matrix outputs on the. Let's take some more coffee. On the shift register. We don't need so much speed on the switch matrix outputs. So it's completely enough to update it, I don't know, every 10 milliseconds. Or only 20. Every 100 milliseconds, it doesn't matter. So we'll add these two. So we'll certainly move them here to reduce the error points. Delete from that and delete from that. And then we have 3 reserve pins that we will simply map to the Raspberry Pi. Maybe we want to add something on the front panel later. Or watch it on. For that I'm completely happy. So that will be reserve 1. So connector reserve 1. Reserve 2. Okay. And we add a connector reserve 3 plus. So I know that they're used for that. So now with that, now we can add the high side to the this register. High side 1. Okay. High side 2. Okay. Now I can add 1, 2, 3, like J1, 2 to 2 to 5, yes. 2 to 5. And we'll put this down below. We'll put this later on, 2 to 5. We'll certainly connect those directly too, because it's here it is an option to do that. The problem is, of course, it's nicer to have it you have to think about it, what's more appropriate. Of course, it is visually way more clear if you if you have the lines directly connected, and you should do that if you can do it. But if you try hard to connect all the wires in this way, there's nothing to be gained. So it's always the thing of, okay, what does make more sense? In this case, although I'm a friend of connecting the pins over nets, it certainly makes more sense to add everything here. So, one was plus 3.1, was ground again. So I think I will do the following. I'll take the ground, move it down, and add that too. Okay. Now everything is connected to ground, that's good. Then we have a 3.3 volts that needs to be connected, and that's connected here at pin 8. Okay, I don't like that. We'll certainly change that here. The problem here is that we have on the one connector we have 3.3 volts on pin 8, and on the other one we have it at pin 7. We won't do this. We won't do this. That's too much of an error possibility. So we will stay as clear as possible with our pin assignments. So 5.5 will be that one. And come on. And we'll certainly connect the cap. That's okay too. But we don't want to make ourselves error prone and change voltages, because we will destroy nothing if we connect 5 volts to our connector reserve. That's completely safe. We would, in the worst case, also only get something that won't work sporadically if we connected it to some sort of data pin, and we would get an error. Maybe some false data, maybe an LED wouldn't light up, but nothing can happen. But if we connect a 3.3 volt device in our safeness that, oh yeah, we can connect it, there will nothing happen, to the 5 volt rail edge, that's done. We won't do this. So we will connect the 3.3 volts always to the pin 8. And stay on and stay safe. Or at least don't give us the possibility to do a dumb error. There are enough dumb errors to be made, so we certainly don't want to add this one. That would be very unfortunate. That would be very unfortunate. So 3.3 volts to pin 8. And 5 volt to pin 7. At least this one. Okay, I'm happy with this. Then 6 and 7 were reserves. Alright. 6 and 7s are reserves. Okay. Good. When we have connected this correctly, we have connected that, as far as I'm concerned, correctly, and that's the point where we'll stop and do something different. No, save it. That would be very unfortunate. Okay, goodbye, Jeanette.